Hello everyone, my name is Dr. Satyanarayan Rao. In this video, we will talk about soil moisture dynamics and how our understanding of soil moisture has evolved from ancient farming techniques to modern science, and why it is complex to answer even a simple question of how does water move in the soil. During ancient times, early farmers and civilizations like in those in Mesopotamia or ancient Egypt, they actually know that when the soil was damp, the plant liked it and the crop would grow better. But however, they had no way of measuring it or quantifying it. It was purely based on an observational technique. Even now today, if you observe some farmers in rural parts of India and other places, they observe the soil or even touch the soil and say this is the soil moisture. So the importance of soil moisture is not a new science. It was understood, but we never had a way to quantify it or to measure it in a scientific way. The study of soil moisture as a distinct scientific field gained momentum primarily in mid-20th century, systematic research only after 1960s. Maybe it could be due to economic interests like early industrialization driven by steam engines and later electrical energy only focused on mechanical and electrical innovations and economic incentives. However, in contrast, the soil moisture as a research was initially linked to agriculture but did not see the same level of industrial investments until much later. And while agriculture was foundational, the scientific study of soil moisture dynamics became critical only as agricultural productivity and water management became very important, especially during the drought and the rise of modern irrigation. And right now it's much more important with our climate change and other natural disaster that we are facing currently, like droughts, floods, and greenhouse gases and other things. And even though it's surprising that scientific understanding of soil moisture lagged behind fields like mechanical and electrical engineering, given its critical role in agriculture and hydrology. For example, the steam engines were well understood, and even how electricity flows had clear mathematical frameworks by the 1800s. In contrast, the first serious attempt to understand soil moisture, how soil water moves scientifically, did not come until the early 1900s. By 1960s, we had a systematic and comprehensive understanding, and right now we have a growing recognition of its importance in agriculture and climate change. And it's very critical. It plays a critical role in agriculture as well as in the global climate systems. We will see one by one with all these topics covered, and by the end of this video I hope you will have an understanding of the importance of soil moisture and how it works and how it is modeled in the current crop models. So let's first understand what is soil moisture. So we know that the soil is actually made of a bunch of particles with sand, silt and clay, and it creates spaces called pores. And these pores are actually tiny reservoir of water, storing water that plants or any organisms can use it. The size and the arrangement of these pores actually determine how much water the soil can hold and how easily plants can access it. So in short, soil moisture is the water that is being present in the spaces between the soil particles, and we have different soil particles known as sand, silt and clay. And the water that occupies the pore spaces between the soil particles are actually not a static, they don't exist in a static condition, but rather they are very dynamic, influenced by different environmental conditions. And also the water in the soil pore can exist in three distinct forms. For example, we can have the water that is under the influence of gravity, where the water, free water that moves downward through the soil pore after, let's say, a heavy rainfall. We can also have capillary water, where the water rises from the groundwater or is held in the soil micropore and the tube-like structures through the surface tension and capillary forces. It's the same as when we put a straw or a tube on a glass of water, we see a tiny rise. It's the same. And it's very important that we have capillary water because it exists in an ideal zone where it's retained against the gravity and still accessible to plant roots. And so soil structure is very important to have capillary water. And we also have hydroscopic water, which is a very tightly bound water that is actually tightly held due to the electrostatic forces, because we know that the soil surface can be negatively charged. For example, clay particles and other materials, they can actually hold water at a molecular level through electrostatic attractions, and so it's held tightly and is generally not useful for plants. And actually each of these three types of water in the soil actually has an important role in the soil water plant continuum. So if you are interested in learning more about soil science, I actually came across this resource by Purdue Extension, and here they have great videos on soil moisture and capillary rise, as well as some of the basic experiments in soils, and even some videos on soil microbiology. The explanation I found was very simple, and they have great visuals and experiments to help you understand these concepts better. I think it's a great starting point if you want to learn a bit on soil science. So to really understand how soil moisture moves in the soil, the water retention curve is a visual way to actually understand these concepts, because it essentially tells us how soil hold on to water at various water content levels. And so here I show you something that is called as the water retention curve for different types of soils. And on the x-axis we have the water content, and on the y-axis we have the soil water potential, which essentially tells me that how much energy is required to extract the water from the soil. So as we know that soil has many pores, and it's like a sponge that holds on to the water through various forces like gravity, capillary forces, or even adsorption. And so when we need to take out water from a sponge, we need to perform some work like squeezing it. It's some kind of similar here. So this is the energy that is required to drain or required by the plant to extract water. And the curve actually tells us that how easily or difficultly water can be extracted by plants at different moisture level. And here this region is a fully saturated region, and this region is known as the residual water content region. And in between we have a linear region where we have predominantly the capillary effect here. And the different color, like the blue color, is for a sandy soil, and it's steep at the start but actually flattens very quickly. And since sandy soils have large pores, the soil drains quickly, and water is also not held very tightly here, and that's the reason we see a vertical line here. On contrast, if we see the purple curve, which represents the clay soil here, we see that the water is held to great extent. So we don't see a vertical drop here, because we have smaller pores, and it has a huge impact on water retention because it's a fine textured soil, and this type of soil can hold on to water much more tightly because of smaller pores and stronger capillary forces, and also the adsorptive forces. And so in general, the steeper the curve, the more quickly the soil releases water, and flatter the curve, the more tightly the soil holds on to the water. And these shapes helps us understand the water holding characteristics of different soil types, and is very important for modeling soil moisture dynamics. So now we understand that what is water retention. Now we will see how we can model it using the popular Genuchten model. Actually, this model gives us a mathematical way to represent how tightly soil holds on to water at various moisture level. Basically, it helps us to actually predict the soil water retention curve for different types of soil using few parameters that we can actually measure in the laboratory. And so the model looks something like this, where the water content is given as a function of residual water content. The residual water content is the driest point where the soil holds on to the last bits of water so tightly that plants cannot extract it anymore. It's in this region actually of the water retention curve. And the water content is also a function of saturated water content, which represents the soil at its wettest state, when all the pores are filled with water, and it usually represents this end of the water retention curve. And alpha is here. The alpha is the air entry value, which tells me the point where air starts to replace water. As soil dries out, the soil pores becomes empty, and then air can go inside and displace the water. And so this is a tipping point. It's called as alpha. This can be actually measured in the laboratory for different types of soil. And also the N. N is known as the shape factor, and it depends on the porosity of the soil. And it reflects what kind of pores we have in the soil, and it's a high value indicates that we have more varied pore sizes. And so it controls the shape of the curve like this, how it falls between different water content levels. Alpha and N are the values that we usually measure it in the lab, and the other parameters, theta S and theta R, together are known as the Genuchten parameter, and it has been quite well thoroughly parameterized for different types of soil that we have in our agricultural fields. And what makes this Genuchten model so important is that it helps us predict many of the aspects of soil water behavior. For example, we can know how much water is actually available to the plants at different soil moisture level, and how much energy plant should spend to extract it. And it helps us to plan our irrigation, when to switch on our automated irrigation device if we have one. And also it helps us to understand how water moves through different soil layers, which is also important for understanding drainage if we have floods, or even groundwater recharge for planning rainwater harvesting. And so it's like a fingerprint of a soil, the water retention curve. So even though it's very successful, it cannot model all types of soil, unfortunately. For example, carbon rich soils like forest lands or peat, these soils have a lot of organic content, macropores. So these macropore can introduce a discontinuity like black holes in outer space. So where there is no continuity of these pores soil structures, and so we don't have the gravity suddenly appears and water can drip into these macro pores, and so this kind of discontinuity makes it difficult to actually model carbon rich soils using Van Genuchten model, and it's actually an important current research area on how to understand water movement in carbon rich soil. But despite these challenges, the Van Genuchten model continues to be used in many of the current process-based models and crop models to understand how water moves in the soil. So after learning about soil moisture, we will see why it is important for the current climate change challenges that we are facing. Soil moisture acts as a key link between the land surface and the atmosphere. Actually, it plays a major role in how water is being exchanged between land and the atmosphere. And we know that both air and soil contains water, the humidity in the air and the soil water. But how this water moves between land and atmosphere depends heavily on the soil moisture levels. For example, when soil has enough moisture, water can either evaporate directly from soil surface, or it can go through plant roots and then through photosynthesis and exit through tiny pores on the leaves, a process called as transpiration. Together we refer it as evapotranspiration. And this is the key process that actually transfers water from land back into the atmosphere. The conditions that control these processes are actually influenced by factors like soil type, temperature, and how much vegetation we have, like the plant cover. For example, on a hot sunny day, a dry soil cannot evaporate much water, and plants may struggle to take up enough moisture, reducing transpiration. This can reduce actually how much water is being exchanged, that can lead to actually hot surface temperatures, which can make even heat waves more intense. On the other hand, when we have heat waves and if the soil is moist, it can actually act like a cooling agent. Soil moisture actually doesn't respond to weather conditions, it actually shapes them, and so it's a very important parameter for understanding the climate change scenario. And what's fascinating about soil moisture is that it has a kind of memory of the past weather events. And if there has been a prolonged drought or dry spell, the soil moisture will remain low, and it takes very long time for rainfall to actually replenish it. And these long dry conditions can actually influence weather patterns weeks later by limiting the amount of moisture available for evaporation. Well, I think we have come to the end of this video. Thank you very much for watching, and I will come back with another video very soon. Till then, stay tuned and thank you again.